In this video, we are going to talk about gas stoichiometry. In chemistry, stoichiometry involves relating reactants and products of a chemical reaction by doing calculations, hence needing to gather numerical information from the reaction. This video will focus on non-reversible reactions, meaning the chemical reaction just goes in one direction. Real-life examples of such reactions include combustion and reactions that involve changing the state of a substance. In any chemical equation and reaction, we have what we call reactants and products. Reactants are the substances that you initially have and are the ones written on the left side of the equation. Products, on the other hand, are the substances that result from the interaction of the reactants. They are written on the right side of the equation. Since we are dealing with unidirectional, non-reversible reactions, we are going to use right pointing arrows for our chemical equations. Stoichiometric calculations involve converting a given variable on one side of a chemical reaction to an unknown variable on the other side. The simplest stoichiometric calculations only involve having to look for the moles of B equivalent to the given moles of A. You just need to look for their mole ratios based on numerical coefficients from their balanced equations. In other situations, you may be given different known variables, such as the mass, volume, or the number of particles of your reactant. You might also be tasked to calculate for the same variables of your product. Either way, the only way that you would be able to connect the two sides of the chemical equation is by using the mole ratio of the concerned reactant and product. Because of this, you are going to need to convert first your given variables into moles of your reactant. For instance, if you are initially given the mass, usually in grams, of your reactant, you're going to need to convert it to mole A using molar masses and stoichiometric calculations. You're going to need to refer to the periodic table for the atomic masses of individual elements. You might also be given the volume of your reactant. In this case, you are going to use the formula for the ideal gas law. Certain problems, however, give out standard conditions, so you also need to take note of this one. Other problems would also give out the number of particles of your reactant. When this happens, you're going to use Avogadro's number and stoichiometrically calculate for mole A. In a similar manner that you calculated for mole A given either the mass, volume, or the number of particles, you would be able to calculate these same variables for B by doing the reverse calculations for each respective variable. Let's now try doing this example. A sample of hydrogen gas has a volume of 8 liters at a pressure of 5 atmosphere and a temperature of 25 degrees Celsius. What volume of water vapor is produced by the following reaction at 150 degrees Celsius and 0.947 atmosphere if all the hydrogen gas reacts with copper 2 oxide? In solving word problems, you need to dissect each statement carefully to understand the context of the entire problem. Usually, in examples such as this one, the first part or sentence sets the initial condition, or conditions for the reactant side of the chemical reaction. It is the one highlighted in yellow. It would then be followed by stating the final condition, or the condition for the product side. It is now the one highlighted in orange. Since we are talking about chemical reactions, you need to write the balanced chemical equation if it's not given. For this equation, I provided the same color highlights that correspond to their respective parts in the word problem. The next thing that you need to do is determine the scheme of what you'll need to solve for in the problem. Remember that you may be given either the moles, mass, volume, or number of particles, and you need to calculate one of these variables as well. Notice that the given variable in the initial condition is the volume of the reactant. Similarly, what is being asked for in the final condition is the volume of the product. Recall that in order to relate the two sides of the chemical reaction given any variable, you need to use the mole ratio of the reactant and the product concerned. Therefore, your scheme would look something like this, where volume A and mole A are for H2, which is the reactant gas, while mole B and volume B are for H2O, or water vapor, which is the product gas. In this scheme, Each arrow represents a step in solving. We begin from left to right, starting with solving for mole A using volume A. We list down all given variables in the initial condition and convert the temperature to Kelvin. Since the given is volume, we are going to use the formula for the ideal gas law. From this, we need to derive the formula for mole A, which is represented by the letter N. Your formula would now look like this. From this derived formula, you may now substitute the variables with their given values. Take note that R represents the ideal gas constant. After substituting, you may now solve for the moles of H2. By solving and canceling out similar units, you would come up with a value of 1.63 moles of H2 gas. This now ends the first step of the solving scheme for this problem. The second step of the scheme now involves solving for the moles of water vapor using your calculated moles of hydrogen gas. We do this by using the coefficients of the concerned reactant and product in the balanced equation. Since H2 and H2O don't have numerical coefficients, it is understood that both their coefficients are equal to 1, hence the 1-to-1 mole ratio. We now multiply our solved mole A with the mole ratio of A and B, putting H2O in the numerator and H2 in the denominator of the ratio to cancel out the unit for moles of A or H2 gas. You would now come up with mole B value of 1.63 moles H2O. This ends the second step of the solving scheme. The final step of the scheme now involves using the solved mole B value to calculate for the volume B or the volume of the produced water vapor. Do this by first enumerating the given variables from the final condition. Take note that the final temperature is converted again to Kelvin. We would again use the formula for the ideal gas law, but this time we isolate volume since it is the one we're looking for. We would then have this derived formula. Substitute the variables with their given values like this, then calculate the final answer. You would come up with a volume of produced water vapor, which is 59.7673 liters. This marks the end of the last step of our solving scheme for this problem. Sometimes, you might be asked to round off your answer into significant figures, so you have to consider that as well. In this case, since the given variable with the least significant figures are these ones, your final answer should have the same number of significant figures, which is 2. Since the number 60 itself has only one significant figure, a workaround that I thought of was to express it in scientific notation. That would then be your final answer. If you have any suggestions for topics, just leave a comment down below. Thank you for watching. I hope that you understood what I discussed, and again, don't stop learning something new every day. Peace and stay safe.